Hello everyone, and welcome back to Electrical Engineering. Today we will continue our discussion of Ohm's Law. We will try to unpack some of what Ohm's Law means. Sure, we can put an equation up on the board, but if you don't understand what it means, you won't be able to master electrical engineering. So with that, let's jump back in. Okay, so last time you were given a problem to figure out. You were given the amount of current flowing through the circuit, and you were also given the amount of resistance in the circuit. The unit of current is called the amp, so there could be 2 amps or 3 amps or a single amp, but they are all amps. And they are labeled with an uppercase A. So in this case, we were told there are 5 amps of current flowing in the circuit. We will talk more about the amp and what it means later. Also, if there is an arrow in the circuit, it tells you which direction the current has to go. Not all schematics will tell you the direction of current, but some will. The current is also constrained inside the circuit, meaning that it cannot leave the wire or components, but rather has to follow them as if they were like pipes. The unit for resistance is the ohm. The ohm is labeled with the uppercase Greek letter omega. So depending on the type of circuit, there might be 50 ohms, 10 ohms, or 2 ohms of resistance. In this case, we were told there are 24 ohms worth of resistance in the circuit. Now we've only used Ohm's law once, but hopefully you got an idea of how it works from last time. We were given the current and resistance in the circuit. This means that we can find the voltage. Basically, the question asks if there are 5 amps of current flowing in the circuit and the circuit has 24 ohms of resistance, how much voltage is required to push that 5 amps of current through 24 ohms of resistance? We do the calculation and find 120 volts. Remember what this symbol stands for? It is a voltage source. Sure enough, that is the source for the 120 volts needed to move the 5 amps. This means that if you know any 2 of the 3 components in Ohm's law, you can find the third. If you were given the voltage and the current, you could find the amount of resistance in the circuit. All right, let's do another example. Let's say you're working on a little project and you want to make a light work. You read on the back of the light bulb package and it says that this light requires 20 milliamps of current. It also says that this light has 150 ohms of resistance. The prefix milli means divided by 1000, so 20 milliamps can be rewritten as 0.02 amps. We want to know how much voltage is needed to make the light work. We multiply the 0.02 amps times 150 ohms, and we find 3 volts is required to make the light work. So we're walking around the hardware store trying to find a suitable voltage source to power our project. We come across a AA battery. We read the fine print and notice it says 1.5 volts. We go ahead and plug the battery into our circuit to see if it will work. Now remember, voltage acts like a pushing force. So by plugging in that battery, we are causing current to start flowing. What will happen? Well, it depends on what type of light we are dealing with. If it's an LED, it probably will not even turn on. Let's say though that we have an incandescent light bulb. In this case, it will glow but not very bright. It will be pretty dim. Why? Well, we only have 1.5 volts and the light bulb requires 3. So how can we fix this? Well, we can just add another battery to the circuit. More current will now flow because we have more voltage. The light will now glow like it's supposed to. This is because we now have 3 volts instead of 1.5 volts, and this light bulb requires 3 volts. What if we were to add another light bulb to our circuit? Could we figure out how many batteries we would need? Yes, we can. So remember the parameters we were given for the first light bulb? It was 0.02 amps and 150 ohms. Well, now multiply that equation times 2 because we have 2 light bulbs. And what we find is that 6 volts are required to run the 2 light bulbs. And by knowing that there are 1.5 volts in AA battery, we can figure out that 4 batteries are needed. And with that, we figured out how to make light bulbs work. It is worth noting here that we are playing a little loosely with the units. As we unpack more of this topic, you will understand a little more about the units that lie behind the process. We just hooked up 2 batteries to our previous circuit. The way we connected them is called in series. We can combine all sorts of components in series, like so. Our components are in series if the same amount of current flows through component 1 to component 2, and so on. So in this case, the current starts in the top left resistor and follows the circuit to number 2, then 3, and so on. Basically, the current will get to each component in a series-like fashion on its path around the circuit. Not all circuits are series circuits. What if we were to divide this circuit with a connecting wire in the middle? Well, the same current that was moving across the resistor would come upon what is called a node. A node is a place where any 2 or more circuit elements have a common connection. In this case, some of the current could go through the top branch, but some could go through the middle branch. This is no longer a series circuit because there are multiple directions that the current can go through. This is what circuit analysis will teach you. You will be able to analyze what a circuit is doing. You will be able to figure out where the current is going, how much voltage is being created, and even how much total resistance the circuit has. Just as with the light bulb example, you will need to be able to figure out the circuit in order to make stuff work, like light bulbs or lasers or guitar amplifiers. Okay, last question. Let's say we had a circuit like the one shown below. Because this circuit has a voltage source, it is going to try to induce current to flow. Will current flow? And if so, how much current will flow? Think about this, and we will look at the answer in the next video. Take care, everyone.